Fred and Francine are disagreeing about who's doing more work. They each think they do the most work. So what's going on? Well, Fred carries 6 books from downstairs red to upstairs red. Francine carries 6 books from upstairs red to upstairs purple. So who is doing more work? To answer this, we're going to talk about the physics definition of work. Work in physics is defined as a force acting over a displacement, d, to cause a change in energy. We're going to talk about energy in this unit, but for now we're going to start with work. The very simple definition of work, which we're not going to use, is work is the force times the distance. Well, it's a little bit more complicated than that. And so we're going to use a better definition of work, which is from the AP equation sheet. And this is it right here. So we're going to get rid of the simple definition, and we're going to focus on, right now, the middle part of the AP definition. So eventually we'll get to looking at the change in energy equals work, but that'll be a later lesson. The work equals the force times distance, but in fact it's only the parallel force that causes work. And that parallel force is the force that's acting parallel to the displacement vector. Let's talk about that in some more detail. First, let me just say that the units for work are going to be the joules, which is a capital G. 1 joule equals 1 Newton times a meter, which is equal to kilogram times meter squared per second squared. These are the same units we use for energy. So the only forces that can do work are forces that are parallel to the displacement of the object, which is what we call F parallel. In this problem, we have a box being pulled by a string at an angle, but the only component of that force that's going to do work is the part that is parallel to the displacement vector. So if you drew this force, the string force, as a vector, you would have its parallel component, or its x component, and its perpendicular component, or its y component. Only the parallel component will do work. And from our trigonometry, that parallel component is equal to F cosine theta. The theta is the angle between the force vector and the displacement vector. So it's the angle between the string and the displacement vector. That's our theta. And F cosine theta will give us the component of the force parallel to the displacement. So we end up with this equation. D is the distance that the object moves. It's not a vector. Well, it is a vector, but in this equation, it's going to end up being magnitude. This has to do with vector calculus, which we're not going to talk about. You just need to understand that the force and the displacement are only given in magnitude. So the D is how far the object travels. So D can never be negative. Requirements for work to happen is that a force or component of a force vector must be applied in the same direction as the displacement, and displacement must occur. So let's see if work is going on in these 3 examples. First, we have a person holding a barbell above their head. They're applying a force vertically, but there's no displacement. Is there work? Let's see. Next, we have a person who is walking with a briefcase. She's holding it with a force up, carrying it at displacement d. Is work being done? We'll see in a minute. Finally, we have an ice skater. She pushes on a wall to the left. The wall pushes back with an equal force to the right. She's displaced to the right. Is work done? We'll see in a second. So first, let's look at the barbell example. Since the displacement is 0, the work is going to be 0. So there's no work done in that example. Next, let's look at the woman carrying the briefcase. There's no parallel force. Her force is perpendicular to the displacement vector. Since there's no parallel force, the work is equal to 0. So no work is done. The last example is probably the trickiest one. There's a force. It goes in the her body is displaced, and there's a force from the wall. Is work done? And the answer is no. The part of the object on which the force acts, which is her hands, actually does not undergo any displacement. So the force is applied, and the displacement is not here. The displacement is her body. So the work done is 0. Now eventually her hands will move because her body will pull the hands. But it's not the wall that's pushing her hands. The wall cannot do work on her because the wall is not moving. So there is no work done for the ice skater either. So let's look back at Fred and Francine. Fred carried books upstairs, and Francine carries books across from one hallway to the next. Who is doing more work? Well, Fred is. Francine is applying a force, but it's perpendicular to the direction of the displacement. So she's actually doing no work by carrying the books. Whereas Fred is going upstairs, he's applying a force up, and his displacement is up. So he is doing work. So he's doing the most work. So work, even though the F and the D are both magnitude, work can be positive and negative. And this has to do with whether energy is being added to the system or removed from the system. Work is a scalar, and it has a positive or negative sign, and the sign says if work is added or removed. So positive sign means work is added, negative sign means it means energy is added, negative sign means energy is removed. So positive work would be adding energy. So pushing a sled so that it goes faster is positive work. Or an engine turning the tires in a car to move it forward, that's positive work. Negative work is taking energy out, so applying brakes to a car, slowing it down, that's going to be negative work. Or friction, if I roll a ball in the grass and it slows down from the friction, that's going to be negative work also. Net work is going to be the sum of the work done by the forces on an object. So for this person who's on a little roller thing with a parachute pulling them, we have an applied force from the string, we have a normal force, we have a force of gravity, and we have a force of friction. The net force on this person is going to be the sum of all 4 forces. I'm sorry, the net force is the sum of all forces. The net work is the sum of all of the work. And in this case, net work is also written as net force times d times cosine of theta.